Today we're going to look at proof by contradiction, an amazing type of proof that can prove things that you otherwise think are not possible to prove. So I'm just going to talk a bit about this. We've spoken a little bit about how a false statement can imply another false statement. That's definitely possible. But actually, false statements can sometimes imply true statements. However, true statements can only imply true statements. So I can't have a true statement and get something that I know is wrong. And in some sense, this is the underpinning thing behind proof by contradiction. What we're going to do is we're going to want to prove something, and we're going to look at two classic proofs to start with, and I think I might just get straight into it. We're going to try and prove by contradiction that there are infinitely many prime numbers. And we're going to assume the opposite. We're going to assume that there aren't an infinite number of prime numbers. And if we can follow along and get something that is false, then we know the original statement was false because it's not possible for a true statement to imply a false statement. Okay, I hope that makes sense. So this is called the negation. We are going to prove by contradiction there are infinitely many prime numbers. Assume there are a finite number. This is what I mean by the negation, the opposite sentence. And then that means we can list them. Okay, we know there's going to be 2, 3, 5, 7, and so on in there, but I'm not going to write that. I'm just going to write the first one's P1, P2, P3, all the way up to Pn. Okay, that's going to be our last one. We can say they're being ordered if we want. Pn is our largest possible prime number. Okay, then we're going to construct a new number based on this. Construct n equal to P1 multiplied by P2 multiplied by P3 and all the other prime numbers up to Pn. So every single prime number it divides into this number we've created. Okay, it's definitely more than the biggest prime number. But we are not quite finished. What we're going to do now is we're going to add 1 to it. So n is definitely going to be bigger than Pn. And Pn was the largest prime. But also P1, P2, etc. do not divide into n. Because they divide into this bit, I'm always going to get a remainder 1 when I divide by P1 and P2 and so on. Okay? So that must mean that n is not divisible by any of the primes. But that must mean that n is prime. Okay, and coupled with the fact that it's not on the list because it's bigger than our primes, and it must be prime, we found a contradiction. How can we have a finite number of primes when I've just discovered a new one? So we say contradiction. If we're being fancy, then we can actually use this symbol. We can put a little X and put these dots in it. That is another word for contradiction. Contradiction, and there are an infinite number of primes, just as a final sentence. What an amazing proof. And some people say this is like one of the sort of top proofs of all time. The fact that you can, through very simple reasoning, show that there are actually an infinite number of prime numbers. Hi. Second proof by contradiction example, and this is just as good as the last one. Prove by contradiction that the square root of 2 is an irrational number. Now, you've been told this ever since you did surge, probably, or maybe even ever since you looked at the square root of 2. It's an irrational number. You can't write it as a fraction. That's what that means. But how do you know? Do you just trust what somebody's saying? What if they just, what if there is one? We've just never discovered it. We are going to prove for absolute sure that it's not possible. So we're going to first of all assume the opposite is true. Assume root 2 is rational. And if we can then obtain something that we know is false, we know that this statement is false, that root 2 is rational is false. Okay, so then we can write root 2 as a rational number as a divided by b. And one other thing we're going to do is we're going to write it in its simplest form. So we're going to have cancelled it down. Like if it was 8 over 4, for example, then I would cancel that down to 4 over 1 or 4. Or 5 over 15, I'd cancel it down to a third. So I can make that assumption because we can always divide through by common factors, basically. So yeah, we've written it in its simplest form. A and b are whole numbers. That's, I'm going to say, it belongs to the set of integers. Okay, that's quite important as well. That's the definition of a rational number. Okay, then, or actually, I'm not going to write then, I'm going to go for my implies symbol. Implies, I can square both sides now. Implies 2 equals a squared over b squared, which implies that a squared is 2b squared. And that implies that a squared is even. It must be because I've times by 2. Now, the only way that a squared can be even is if a is even. And that's a slight leap of faith here. Okay, we're gonna show that in a bit actually. You just have to trust me on it now, but I hope you sort of get a feeling for where that's come from. It's not possible, to get an even because I'm multiplying a by itself. How can I have a factor of 2 there but not 2 factors of 2? Okay, and the answer is that yes, actually a must be even as well. So we're then going to write a equal to 2 times c. Okay, because I know a is an even number, I can write it as 2 times something. Then it's going to be that 2c all squared is 2b squared. We can expand this out. 4c squared is equal to 2b squared. And therefore, b squared is going to equal 2c squared. And for the same reason, like for the same sort of argument, b squared must be even. And b must be even as well. Now this is an issue because we said at the start we'd written it in its simplest form, and now a is even and b is even. So I've not written it in the simplest form, and the only logical argument is that it's not possible to write it in this way because I'd have to have both a and b equal to even. Not possible. Since a and b have no factors, no common factors. So we have a contradiction. Root 2 is irrational. Okay, and actually the same sort of argument will apply for root 3 being irrational, and I'm going to ask you to construct proofs along a similar line. Before I move on, I just want to quickly talk about root 4. What would happen? We know that root 4 is equal to 2, so it can be written as a rational number. What if I try and do the same thing and prove that it is an irrational number? Then I would just change some of these. I would change this to a 4, a change this to a 4, and then I'd get a 4 here, and then this would become a 4 here. But notice I'd know that a squared is a multiple of 4. Okay, that's true. But that wouldn't mean that a has to be a multiple of 4. I'd still only get that a is even from it. So I could then write a equal to 2c. Okay, and I do the same sort of thing. Oh, but I need to change this to a 4 now. And I change this to a 4. And then I'd get that b squared is equal to c squared. So you can see the proof is taking a slightly different form when I'm trying to prove something that is actually I'm trying to prove something. I've taken the opposite, that root 4 is, well, I'm assuming that root 4 is irrational, and I'm not going to find an issue basically, because then I don't have this statement here. I just have that b squared is equal to c squared. So what does that mean? There's no problem with this. We haven't found a contradiction, and the reason is that there is no contradiction. Yes, a has to be even, but b can in this case be odd, and that would actually work for it. So I just wanted to talk about why it will work for some numbers, okay, like root 3 and root 7. It'll be a very similar argument, but if it's a root of a square number, we won't get the issue we have. So I hope this proof by contradiction idea is making sense. We want to prove something, we assume the opposite, we get something we know is false, and that tells us that the thing we started with must have been false as well. An amazingly powerful idea, and we've done 2 absolutely classic proofs, which prove things that you think are really hard to prove, but you just do so in just a few steps actually. Okay, we're going to look at 2 more because it is just worth talking about how these are sort of simpler statements, and you might even say they're intuitive, but we need to prove them really to be sure about that. So the first one actually is this assumption we'd made before. It's given that n's an integer, proved by contradiction. If n squared is even, then n must be even. I sort of argued it before, but we're now going to prove it by contradiction. So assume n is odd. Then n squared, okay, then if n is odd, then I can write n as 2k plus 1, because that's the definition of an odd number. Then n squared will equal 2k plus 1 squared, which will be 4k squared plus 4k plus 1, which is actually 2 lots of 2k squared plus 2k plus 1, which is odd. Okay, because it's again in the form 2p plus 1. But I've assumed but I know that n squared is even, and I've just shown that it's odd. So this is a contradiction, since n squared is even. So therefore n must be even. Yeah, I know it's a whole number. I've said that at the start. So if it's not odd, it must be even. That's the only other thing it could be. Okay, our last example is to prove by contradiction that there is no greatest odd integer. So what we're going to do to start with is we're going to go with the negation. Assume there is a greatest odd integer. And let's call it, what should we call it? Let's call it L. And since L is odd, L equals 2m plus 1 for some m, which is an integer, being really technical. Okay, let n equal L plus 2. So there's nothing stopping me mathematically to add 2 to something. And then it will equal 2m plus 1 plus 2, which I can then write as 2m plus 1 plus 1. I've just factorized the first and the last term. Okay, so n is going to be greater than L, and n is odd because it's just 2 times a number plus 1. But this is an issue because I've assumed that L is the greatest odd integer, yet I've just found one that is both greater and is odd. So this is a contradiction, and I can then just say the last bit, there is no greatest odd integer. Okay, so I think if I'm going to summarize these 4 examples and the idea of proof by contradiction, I can kind of prove obvious things by contradiction, and it's worth just being careful with this and don't just say I know it's true. Okay, think about doing the opposite and getting a contradiction. And I can also prove things that are definitely not obvious. How do we know there's infinitely many prime numbers? Well, you can't check every single number in existence, but we've shown through an argument that there must be an infinite number. Same goes with root 2, and this sort of starts a bit of maths actually that you can extend. I mean, we're not going to go into it, but the idea of proving that pi is irrational, for example, proving other things such as that, they're amazing sort of ideas, that amazing facts as such that we can prove by contradiction. But focus on these 2 ones. These are 2 proofs that you are expected to know. And then other ones that might just crop up are ones a bit like this, or other sort of scenarios, and then you're trying to get something you know is wrong, and you can finish the proof. Okay, thank you for watching, and I hope this all makes